Awesome. So I think the first thing to mention before we introduce the speaker is just a reminder that next week we'll have Jabru who's going to speak. And this will be a very big, I think a very big and very interesting presentation. We'll be very happy to have her. But in the meantime, we have another great speaker called Maria Chang, who is a research scientist at IBM Research AI, specializing in knowledge representation and its applications to NLP, especially NLP understanding tasks. So she has worked in the intersection of AI, education, cognitive science, and investigating sketch and dialogue-based intelligent tutoring systems, as well as neural characteristics of developmental disabilities in children. Maria has a PhD in computer science at Northwestern University and a BA in cognitive science at UC Berkeley. So with that, I would love for you to begin, Maria.
Thank you, Keith. Can you hear me okay?
Yep.
Okay, sounds good. Yeah, thank you for inviting me here. It's my pleasure to share some of our ideas and progress behind inducing complex event patterns from natural language. As Keith mentioned, I'm from IBM Research AI, and I'm going to be talking about work that from a lot of my colleagues and also some collaborators at Northwestern University. So let's get started with, let me just minimize this, with the motivation for this work, which I think we can all agree on, that natural language understanding requires the ability to represent and reason about events. And this is not just something that applies to texts that are explicitly event-driven or procedural texts. This is also applies to pretty much anything, even in domains that we might consider to be really fact-driven, declarative knowledge. We still have to understand the way events persist over time and the way events that we experience in our everyday lives unfold in typical fashion. So our objective is to build systems that can understand events described in natural language to support a variety of downstream tasks, such as learning by reading, question answering, and decision support. So I have sort of three broad sections to this talk. First, I want to talk about some candidate event representations and reasoning techniques that we've been exploring. This will not be by any means exhaustive, just to give you a flavor of the things that we're working with. And then I'd like to talk about type level event patterns, the types of things that we may be able to induce from representations that may be useful for downstream tasks. And I'll talk about some of those downstream tasks to conclude. Okay, so let's get started with an example of what's in an event and what kind of information we want to include in a semantic representation of such an event. So let's take, for example, the NCAA Division I women's basketball tournament, which is currently underway. It is a little bit more prominent in the news this year because last year it was canceled as a result of the pandemic. But if we can kind of go back to like our 7th grade, English class and think about the who, what, where, when, why, how questions and how those can capture what we care about. So for this tournament, who's involved? NCAA women's basketball teams. What are we talking about? It's a sporting event. Where does this occur? San Antonio, Texas. This year it happens to be in one place because of the pandemic. When is this happening? This is not an instant, it's an interval spanning over multiple days. And why? For entertainment, money, prestige, and how? It's going to be a process of elimination over several individual games. So certainly, not all the details that exist about this event, but kind of the core ideas that we may want to capture and that we would expect a human level reading reading system to be able to to understand by reading, like, say, a Wikipedia article about this event. So where we can get this information, we have different sources of knowledge for this, with varying levels of expressivity and structure. So if we take the Wikipedia article for this tournament, it's expressive, it's plentiful, it's unstructured. The article has over 3,000 words. There are maps, tables, brackets, because it's a tournament. But on the other hand, if I look up the Wikidata entity for this event, we have something that's highly structured. We can do RDF reasoning over it. It's less expressive, and if I went in there and counted all the triples that were in Wikidata about this tournament, I would find around 16, just based on the query from a couple days ago. And some of this information is useful. It's an instance of a tournament, and because we have the type hierarchy in Wikidata, we can make inferences based on that. But then there's also a lot of sort of like bookkeeping metadata that for practical matters is useful, but don't necessarily add to the semantics of the event. For example, the Google Knowledge Graph ID of this event, it's just useful for linking to other data sources, but doesn't really give us the kind of who, what, where, why, how information that we actually care about. So the question then is either how do we get some representations that are in between these two extremes, or how do we extract more structured representations from natural language? So 3 candidates for this. We've been looking at 3 different types of representations. The first is what you might consider the target representation for your classic direct information extraction approach, where you have a supervised learning, a directly supervised learning, or a weakly supervised learning setting, where you extract explicit mentions of entities, events, and relations from the text itself. And the inference capabilities are typically very limited for these types of representations. They're very useful because you have this notion of provenance, you know exactly where it came from, but any kind of structure depends on the target vocabulary. But nevertheless, there are many very powerful information extraction systems, so it's worth looking at these representations. Also, we have semantic parsing into abstract meaning representation. And I'm sure many in the seminar are deeply familiar with AMR. But for those who are not, basically it's a semantic representation that represents the tagline is, who's doing what to whom in a sentence. And the advantage of AMR is that there are many robust AMR parsers available. But reasoning over this formalism is also somewhat limited. It's not what you would consider your typical semantic web reasoning or logical reasoning. And then the third type of representation that I'll talk about briefly is predicate calculus using NextKB. Now, NextKB is a knowledge base that's derived from OpenPsych, and it also includes information from FrameNet and VerbNet and WordNet. It was developed at Northwestern University, hosted by Northwestern, openly available, open license. It's very expressive, but harder to extract from natural language than, say, event mentions or semantic parsers. So I'll talk briefly about what I mean when I'm talking about explicit mentions using the sort of classic information extraction approach. So let's take this sentence, for example: juvenile charged with bringing bomb to school. You can tell by the syntax of the sentence, this is like either the opening line of a news article or the headline. In an information extraction system, one of the tasks is entity extraction and entity type extraction. And basically what we want to do there is find the relevant entities in the sentence and assign type labels to them. So in this case, the juvenile is a person, the bomb is a weapon, and the school is an organization. And these labels can come from whatever your training data set is. In this case, we've worked with the ACE data set, also the ERE data set, and I have some citations at the bottom of the slide for approaches that my teammates have developed for extracting entities and event triggers. So we have these different labels, and then in addition to the entities, we can identify event triggers. So the verb charged corresponds to an event, a justice charge indict event type, which has a defendant argument that is juvenile, the same juvenile that's been identified as a person. Similarly, the bringing verb corresponds to a movement transportation event that has the juvenile as the agent argument and the bomb as the artifact argument. Now, in this particular example, which comes from our one of our IE systems, it fails to identify the school as the destination of the movement event. But this is a trained model, so it doesn't detect everything. But in any case, we have the entities, the events, the arguments, and then we also have used the mattress data set, which is a temporal relations data set, in order to look for temporal relations between events, namely before and after relations and vague and equal relations. So in this case, the system finds that despite the fact that charged is mentioned before bringing, charge happens after the bringing event. So these are the types of things we can extract from text automatically with a trained model. But then what aside from being able to directly querying this information, what other kinds of implicit information can you get from this? Well, this depends greatly on your target vocabulary. So as I mentioned, we're using ACE dataset, ACE 2005, and this has 8 event types and 33 subtypes. So just with that, you can do some very light taxonomic reasoning. And what I mean by that is, say you have a matching process that you need to do, and you have a underspecified justice event, and you have a charge indict justice event. Well, based on the fact that one is a specialization of the other, you can use that to inform your matching process. So reasoning, you might want to put quotes around that, but it is something that you can do based on your vocabulary. And then similarly with temporal reasoning, because we have these temporal relations which are transitive, you can use basic graph algorithms to look for the deductive closure and for looking for inconsistencies. So specifically, if you have a cycle of before relations, that doesn't make any sense, because then you'll have something that's both before and after, and so that's one way to look for contradictions. And we've used that in sort of filtering out all the different temporal relations that we have. Okay, so moving on to abstract meaning representation. That same sentence I mentioned before, the juvenile charged with bringing a bomb to school. On the right-hand side of this slide, this is the AMR parse for that sentence. And for just briefly, if anybody is less familiar with AMR, basically this breaks down into a graph the different roles of this charge event and the bring event. So it basically says that a juvenile was charged with bringing a bomb to school, and you can see that the arg0 of bring, the primary agent for bring, is the same as the arg1 for charge. So the person doing the bringing is the same as the person who's been charged. And the advantage of using AMR over something like the explicit mentions that I showed previously is that you have the representation is intended to be domain general. So I know that in practice, many times AMR parsers are sort of fine-tuned to a particular task, but in general, it's not intended to be a domain-specific thing. You're supposed to be able to to use the same vocabulary across different domains. And
A question.
Yes.
Is that arg2 school supposed to be arg2 of bring, not of charge?
I think it's just an indentation issue. So
yes, you're right. Yes, thank you. Yes, thank you. It's an indentation issue. That's a copy paste, like a total copy paste error thing. But yes, good catch. It's supposed to be, bringing to school, not charged to school, or charged with. I guess this would be charged with school, but yes, you're right. Right. So the vocabulary here is much bigger. You have compared to, say ACE, where we only had like 33 event types. If you think of the verb frames as being event types, there's over 10,000 verb frame senses. And in terms of the roles, another nice feature of AMR is that they have these numbering conventions that sort of open the door for cross-frame generalization. What I mean by that is that in general, the arg0, no matter what the verb frame is, it's going to be talking about the primary, like the agent of the doer, so to speak, of that verb frame. Arg1 tends to be like your direct object. And then as the numbers increase, it gets a little bit less consistent, but there are conventions across the different verb frames. And in terms of reasoning over these structures, I believe there is some work on exporting AMR into like a linked data format so that you can do RDF reasoning over it. But we've experimented with doing, with basically analyzing the paths in AMR graphs in order to do knowledge-based question answering. And I have a citation on the bottom from some of my colleagues where we've worked on analyzing AMR graphs for the purposes of parsing natural language into Sparkle queries. And we use this to achieve state-of-the-art on LC-Quad and QALD. And this is a preprint is available for now. A little bit more detail on that. So knowledge-based question answering, for anybody who's not familiar with it, the basic idea is you take a natural language question and the task is supposed to be to retrieve an answer from a knowledge graph for that question. And oftentimes the task can be reduced to translating a natural language question into a Sparkle query, because once you have the Sparkle query, then getting the answer from the knowledge graph is just a matter of executing that query. So we, in the citation shown below, we introduced a sort of modular system of systems paper where we take an input question and we get the AMR parse from that, and we use an entity linker to link named entities in the AMR parse with URIs in our target knowledge graph. So for example, this question here, which actors starred in Spanish movies produced by Benicio del Toro, produces the following AMR graph. And we have two entities with names. One is a person, Benicio del Toro, and the other is a country, Spain. And these are linked to the DBpedia entities, Spain and Benicio del Toro. So you can think of this as sort of like a URI enhanced or a DBpedia-ified AMR parse. Now we take these entities and construct a path between the entities and our target variable. Now the target variable is going to be either an AMR unknown node, which is the way AMR represents questions, or it's going to be one of the arguments of like an imperative verb frame. Like sometimes the questions are not explicitly questions. Sometimes the so-called questions will say something like, list all the actors in best pictures of blah, 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 or give me blah, blah, blah. And so in that case, we need to look at the arguments of those imperative verb frames and detect the target variable from there. But in any case, the path between the target variable and these entities act as a sort of candidate graph of what belongs in the final where clause. So then we take those paths and we attempt to match them to the results of a relation linking service. And the relation linker is going to return relations that may span multiple AMR edges, because the granularity of the relations in the knowledge graph doesn't have anything to do with the granularity of the relations in AMR. So we have to be able to collapse paths if needed. But the idea is that when all said and done, we end up with a graph that represents the triples that go in our final Sparkle query. And so in that sense, we're able to use the AMR parse in order to get to our final Sparkle query and then answer the question. Okay, so that's about how we extract and use AMR. The third type of representation I want to talk about are relational representations in NextKB. As I mentioned before, NextKB is a knowledge base coming out of Northwestern that's derived from OpenPsych. And the way events are represented in this formalism is actually quite similar to the way they are represented in AMR if you were to translate an AMR graph into a set of triples. So basically you have the event is reified as an entity, and then the roles of the role fillers of those events are represented with binary relations. But an important difference is that each of these event types and role relations are connected to the NextKB ontology. And so to give you an example, we have three different representations, three different events represented here. The first one is a creation event, and then we have these different roles for the outputs created location. This one is a destruction event, and then there's a movement event. And these not only are the types connected to the ontology, but also the role relations as well. And so what I mean by that is that you can find an ontological connection between, say, an absorption event and a movement event by virtue of the fact that those are both specializations of a transfer in event. This is a concept from OpenPsych. But also that you have these different role relations. Object acted on is a specialization of pre-actors, and to location is also a specialization of pre-actors. And pre-actors is kind of an abstract role relation that denotes actors that are known to pre-exist, like the temporal existence of the event you're talking about. And so we use these representations for predicting state changes in procedural texts. This is basically a task of determining what, given passages about different processes, where certain participants are at the end of the process, whether or not they've been created or destroyed, and so on. And this is evaluated using the ProPara data set from AI2. Okay, so those are some of the candidate representations and reasoning techniques that we've explored. Now I want to talk about the type level event patterns. So going back to our NCAA example, if we go up one layer of abstraction and talk about this being a generic sporting event series, and we want to answer these same questions about them, the who is involved becomes a bit more general. Now we're talking about sports teams. The type is more general. It's a generic sporting event series. Where may this happen? This could be happen over multiple, possibly spatially disjoint locations. The interval could be intermittent over several days. Why kind of stays the same: prize money, titles, prestige. How also similar, a series of games and matches to eliminate the team. So the answers to these questions are pretty much of the same flavor, but slightly more general in most cases. So then the question becomes, what are how do we induce this type of knowledge from some of the representations that I mentioned earlier? And there's different types of pattern information here. One type of knowledge is what are the typical role fillers from of the different events that are occurring. And one idea we have is a very straightforward idea is, you can aggregate AMR parsers across different sentences in an attempt to reveal patterns in the role filler types. So consider the following sentences. You have a juvenile charged with bringing a bomb to school, the same sentence I had earlier. And then another, apologize for background noise. And then another sentence about bringing a gun onto the academy's campus. And then a third sentence where bringing is used in a slightly different way, bringing him to justice. And then lastly, bring the perpetrators to justice. So actually in the resulting AMR parsers for these sentences, the same bring verb sense is used throughout, but as human readers, we can see that these are slightly different uses. They're the last two sentences are more of a kind of metaphorical use of the verb bring. So let's take a closer look at these. The first two sentences, I have a sort of the sub graph of the AMR parse. Just for brevity, I don't have the whole thing here, but just the graph that corresponds to the use of the bring 01 verb frame. So this is the part of the parse that describes bringing a gun to campus, and then the other sentence, bringing a bomb to school. So if we collapse these things or we aggregate them along their common arguments, we can sort of summarize these two in the following way. We can say that these two together represent a person or a juvenile bringing a gun or bomb to campus or school. Now, if we're relying on just strict identicality, you can see that this isn't really, there's not really any kind of compression happening, or there's no summarization happening here. We're just kind of putting everything together in a big disjunction. But if we did even just really simple or some very basic taxonomic inference, we could probably collapse these even further. Basically, well, we know that a juvenile is a subclass of person, so maybe we could just put person here, and maybe we can replace this with weapon, and we can replace this with facility or location or organization or something like that. In contrast with bringing something or someone to justice, these two variables, P1 and P2, in another part of the same parse, identify these variables as being instances of person. And these two types here are also identical. They're both justice. And you may notice that the first sentence only has an arg1 and an arg2, whereas the second sentence has arg0, arg1, and arg2. So we can collapse these by saying, like, okay, well, a person or some unknown brings another person to justice. And so here, even with like, identicality, we're still able to make some kind of very, basic generalization here. So that's one idea for using AMR to arrive at some typical role fillers. A slightly different pattern that we're also interested in is typical event sequences. And so for this, we're using something called graphical event modeling. And the idea with graphical event models is that it's a framework for a mark point process where the rate of a particular event type depends on the historical occurrence of the parents of that event type in the graphical model. So, for example, this timeline shown at the top is just an illustrative timeline from a healthcare event stream. So let's say you have these three different event types occurring at irregular times throughout your stream. You have a prescription refill, a hospital admission, and a home health visit, and these are happening at irregular intervals throughout as time moves on. And given a large event stream, the graphical event model can build a model of these event types and hypothesize basically the dependence relations between them. So here's an illustrative graphical event model for this event stream. And what this basically says is that a prescription refill, the rate at which a prescription refill occurs, will depend on the historical occurrence of other prescription refills, because it has this loop, and also the historical occurrence of hospital admissions, because it also has an incoming edge. And then prescription refill influences hospital admission, and hospital admission influences home health visit. So this is useful for things like prediction and for discovering causal relationships, or even just statistical relationships between different event types. And one newer formulation of a graphical event model that some of our colleagues have worked on is called an ordinal graphical event model, where you have not only the just the binary occurrence of a parent in a graph, you also have the different order instantiations possibly affecting the rate of an event type differently. So for example, a prescription refill, because it depends on both prior prescription refills and hospital admissions, what an OGEM allows you to model is to say that, well, if you have a prescription refill followed by a hospital admission, that may affect the rate of a prescription refill differently than if you have those two parents happening, in the opposite order. So we've used these graphical event models, ordinal graphical event models, to fit event streams in political, healthcare, and employment data sets. And we then started to think about, well, is there a way that we can combine these two different, very different approaches for putting together an event representation that takes into account typical role fillers and typical event sequences? And so that's something that we started to explore with text documents, specifically news and Wikipedia articles. So here's an example of how that sort of pipeline might work. On the left-hand side, I have an excerpt of the Wikipedia article describing the Boston Marathon bombing. It describes two homemade pressure cooker bombs detonated 14 seconds apart. There was a kill, there were casualties, so there was a killing event. And then it later describes that one of the perpetrators abducted or took someone hostage and told that person that he was responsible for the attack. So what we do with documents like these is we generate AMR parsers for the sentences in the document. And then we do this AMR aggregation that I described earlier, again, using a very simple identicality-based approach in order to find specializations that are very frequent in our particular corpus. So for example, we see many occurrences of the detonate verb frame. And in virtually all the cases, the arg1 is an instance of bomb. In the other cases, or actually, no, also in those cases, the arg0 could be a person, it could be an organization, it could be a terrorist, a military, or instance of military. And so what we can do is we can say, okay, well, when we're generating a event stream of our observations, rather than just saying, okay, we've observed a detonation, we can say we've observed a bomb detonation. And then we can hold on to the distribution of the other arguments if we wanted to make any kind of prediction about, who are the agents that may be involved. So given those specialized events that we extract from the documents, we then generate what we call a naive event stream. And it's naive because there's not always times. There's a timestamp associated with some detonation, but there are other events such as the telling and the taking that don't have timestamps associated with them. So we just put them in the order in which they occur within the document. This happened to be before we built our temporal relation extraction model. So it's a naive event stream, just sort of as a proof of concept. Nevertheless, we can run the GEMS model on these event streams and attempt to find sequentially dependent event types. And we call these things event chains. And so these are event types that frequently occur together and frequently influence, the occurrence of another event type in the stream. So with this event chain, detonate bomb, kill, tell basically says is that the detonate bomb is frequently followed by kill and frequently followed by tell. And this is the potentially useful aspect in terms of finding typical event sequences, whereas this is the useful part in terms of finding typical role fillers. And then we can export this to RDF for downstream reasoning if we want. But this is sort of the initial pipeline that we looked at in order to see is this something that can be done to find these patterns from text without explicit labels for what those patterns might be. So we ran a small experiment using this approach on 183 news and Wikipedia articles describing IED attacks. We found 31 event chains, for example, arrest followed by convict, detonate followed by kill, followed by tell. We also found some that that seemed a little bit strange. We had and that indicate the possibility, or that are as a result of the possibility of having self loops in the graphical event model. For example, we had detonate, attend, which seemed a little bit strange. Detonate, try, detonate. Maybe that makes a little bit more sense. But again, as a proof of concept, and this is without any labels related to the patterns that we may be looking for. And then in terms of role filler patterns, we found 54 AMR frame specializations that were particular to this corpus of 183 news and Wikipedia articles. So for example, we found things like attending a meeting rather than just attend, expressing condolences rather than just express, try to detonate rather than just try. And as you can imagine, these specializations will probably depend heavily, they will depend heavily on whatever corpus you're looking at. So this was of interest to us because if we're dealing with or we want to build an application in a specialized domain, perhaps there are not that many documents available, we don't know what the patterns are, this could be a useful way of finding those event specializations. Okay, so I'll sort of start to conclude now with some of the opportunities for using this information for downstream tasks. I want to make a distinction between general background knowledge that may or may not be induced and the type of symbolic knowledge that we're looking for with typical role patterns and typical event sequences. So, the latent knowledge in language models is certainly a form of background knowledge that's useful for various downstream tasks, especially information extraction. So the models that I mentioned earlier for extracting entities and events and relations, those all rely on language models. And so that's a key way in which this background knowledge is used. Another way that I didn't go into detail about is using knowledge graph embeddings to improve natural language inference. And we had a couple of papers on that where we used embeddings from ConceptNet in order to improve performance on SciTail and MNLI natural language inference data sets. Slightly, so more related to what I was talking about with GEMS and AMR, the event patterns or the event chains that we extract from ordinal graphical event models are certainly useful for fitting these different data sets in different domains. But even more explicitly, you can use them to discover these causal relationships between event types, and one can see how that would be very useful for applications like event prediction and decision support. And then also the next KB representations that I mentioned for predicting state changes, those were used to induce event patterns in the form of what they call query cases. And this works in an analogical question answering setting where the query cases are kind of used as sort of like cases in a case-based reasoning system, where you have a process being described and you know that from your training you have a very similar, structurally similar process, and therefore you can transfer the inferences from those training cases into the current scenario. And that was used for answering questions about state changes in the ProPara data set. So to conclude, we've explored different event representations with varying levels of expressivity and varying levels of extraction and parsing difficulty. And each of them lend themselves to different types of analysis, or one can call it analysis or reasoning, or different methods of pattern induction that serve different purposes. So for AMR, we're seeing that we can use those to detect patterns in common role fillers. But for things like event mentions, if we can put them into partial orders using temporal relations, then that means that we could feed that we could possibly feed that information into graphical event models so that we can detect causal relationships. And these are initial experiments by combining these different representations are encouraging, because we're able to discover things that that don't rely on explicit training data for the types of patterns that we're after. And so for future work, we're looking on applying this approach to other decision support and natural language understanding tasks, like learning by reading and others. And just in general, we're as a group, we're interested in human level learning by reading and natural language understanding more generally. So anything that helps us get closer to that is something that we're interested in. So that concludes the technical portion of the talk. I just want to acknowledge the broader team, neuro-symbolic team at IBM Research. I have, I assume that we can share these slides afterwards so you can get the URLs from this, but if you're interested in learning more about what we're working on in terms of neuro-symbolic AI at IBM, please check us out. These are some of the papers that I've referenced earlier in the talk on information extraction and KBQA and natural language inference and graphical event modeling. And also I want to acknowledge our collaborators at the Qualitative Reasoning Group at Northwestern. If you're interested at all in NextKB, it's open license. The URL is here. You can also just Google NextKB Northwestern and feel free to check it out. And I'm happy to discuss offline about any questions about that. And also want to acknowledge DARPA. This work is partially supported by the Kairos program. And then lastly, if you're interested in neuro-symbolic representation and reasoning over natural language, and you have something that you think will be ready to go for May 1st, please check out our upcoming IJCAI workshop, neuro-symbolic natural language inference. We're focusing on natural language inference as a candidate task, but really we're interested in neuro-symbolic representation and reasoning over natural language in general. So if there are other tasks that that you're working on that you feel might be relevant, please check us out. So that's it. And at this time, I'm happy to take questions or engage in discussion on any of these topics. Thank you.
Awesome. Thank you, Maria. For those who are here, do any of you have any questions about what the talk?
Sure. Thanks for a nice talk, Maria. So when you're building these, and in the process of figuring out the OGEM model and that you want to combine roles in one way or use AMR or not. How do you guide your work to know whether you're doing a good job at
That's a
finding
great
patterns?
Yeah, that's a great question. And frankly, something that we struggled with. So there's a couple options. One is to choose a downstream task where there are already metrics such as KBQA or natural language inference or something like that. The other thing, and because we're both in the Kairos program, so this is more relevant to that. The other thing that we're considering is, what is a data set that we can construct from data that's already out there, like on Wikipedia or Wikidata, where we can basically do something like event masking is kind of what I'm imagining, where you have, this is the partial information you have, and this is the stuff that we think you should be able to fill in. These are the gaps, these are the blanks that we think you should be able to fill in based on some background knowledge. Can you do that after doing this kind of induction? But frankly, yeah, it's something that we struggled with in the past year, and we're definitely still brainstorming things for measuring that accurately. But so far, the easiest thing to do has been, take a downstream task like information extraction or KBQA or natural language inference, and see if whatever we're doing helps those those end numbers in any way.
Thanks. I have follow-ups, but I want to wait to see if anybody else has a question first.
Sure. Do other people have questions before John asks his own? Maybe you should continue, John.
Okay, great. So another question is, so I know you seem to use AMR a lot, right? If I understand properly, AMR is ties into the that prop bank. I always get confused about things. But I wonder, did you explore? So presumably, you like the ability of AMR parsers to do sense disambiguation better, perhaps, than other approaches. I wondered if you tried, say, FrameNet parsers instead, or other means of sense disambiguation.
Yeah, not extensively, no. So in the work that I referenced on with NextKB, it uses a rule-based parser that uses some elements of FrameNet, and with that, we've had better success working with simplified English. Pretty much all the experiments I've run with it have been on simplified natural language. So we have had success with AMR, but we are certainly open to using other parsers for that purpose. And if you have specific recommendations, I'd love to hear them.
No, that's just the opposite. I'm fishing, so thank you. Great. No, this is really helpful. So another problem that we've encountered is when trying to find interesting sequences, that we get a lot of meta events that are kind of about the events that are consumed with the reporting of news, which is often what most of the information is. So you get a lot of said and reported and claimed and denied and objected. And I wonder if you take specific actions to only find these kind of important to committing crime kinds of events.
Yeah, that one's hard because we don't want to tailor to a specific scenario or domain too much. And actually, what we've done so far is, instead of focusing on filtering specific event types, we instead try and find the important characters and then just include whatever events involve those characters. But I share your concern, especially when I would look at some of the entity extraction results, and some of the entities would be the reporter, you know what I mean, or the Associated Press and things like that, just artifacts from the type of documents you're looking at. But Yeah, so
Also,
far
correct becomes a problem, right?
Yes, exactly. So we focused on characters so far, but I will say that one opportunity that I think was missed, and we need to, and we should explore this now, is, not ignoring the fact that you don't come into the task not knowing anything about what you should be looking for. So we took the information extraction approach that was just came into it like, look, these are the vocabulary things that you're looking for. Just go find what you can, as opposed to, we have an idea that we're kind of looking for outbreaks, or we're kind of looking for attacks or something, and then using that to guide our IE. And that's something we want to do next for sure.
Thanks. I see Ulf has a question.
Yes, thank you very much. Very, very nice talk, and I'm very happy to see AMR applied.
Great.
From your perspective, if there's one thing that could be improved for AMR, what would it be?
Oh, that's a great question. That's a great question. So I would love to see sort of like an abstract AMR representation, or abstract meaning representation, where you have something more on the document or corpus level. I've seen, and I'm maybe missing other work, but what I've seen on multi-sentence AMR seems to be, you just have multiple sentences in the same parse, and there's some co-reference happening. But if you have a corpus where you can rely on some kind of redundancy, then maybe we can take advantage of that and have an AMR that describes, like a narrative, as opposed to something that's so closely tied to the sentence. And then there are other things like, but they might be outside of the scope of AMR, like like tense and the things that are like known limitations. But I think for analyzing larger corpora, where there are redundant documents that describe the same thing, it would be tremendously useful to have a higher level AMR parse that describes, just sort of a narrative, as opposed to the elements of these individual sentences.
Okay, very interesting. Thank you.
Great.
So,
sorry, please continue.
So what AMR parser do you guys like? We
have one that we built, the Stack LSTM AMR parser. They're spinning out new ones all the time. So that's the one that we have been using. I can share. I'm not on the team that's building the actual parsers, but we always use the ones that are in-house. So I can share those. I can add some references to that on these slides before I share them.
Great.
Yes, thank you. Actually, feel free to email the slides to me, and then I'll be happy to share them on our Slack channel. So that would be very, very useful. Thank you. Okay, so does anyone else have any other questions?
I have a brief question. Again, very nice talk. Thank you. When you started out with your event representations, you were talking about next KB. And what struck me there is that you were talking about hierarchies, sort of taxonomic hierarchies of events. And I know that there's some views in the community that events generally don't really taxonomize that well, not in the same way, for example, as entity types do. And the example you had there had some very, very general roles, such as pre-actors. And I'm just curious if you actually find that you get some useful inferences from those very high-level event types, as opposed to getting noise, which you might actually get when you run this over somewhat noisy data that comes from natural language extraction. So I'm just curious what your experience is there.
Yeah, that's a great question. In that particular case, you basically use the fact that you have training examples to try and highlight the relevant paths for you, so that you don't use everything that's already in the in NextKB. But you're absolutely right. Once you get a couple levels, you can't do something like, okay, these two things can be matched to each other if they share a common parent 2 levels up or something, because you immediately or very quickly you get into things like partially tangible or spatially temporal, or these super high level categories that that don't help you. So it depends. I mean, it's a real problem that you have these very, very general categories and predicates that can encapsulate so much. But I think the key in that in this work by Danilo Ribeiro is that you basically use the fact that that two items go together in training, and then you find the commonalities between those things, so that so that you don't have to use all the noise that's already there. You already have like a signal from the training data. So I've had mixed experience with that.
Okay, thank you.
And thank you for that question. Are there any other questions that people have? All right, with that, I want to thank you again, Maria, for this really excellent talk. This was a very, very productive Q&A session and a very, very interesting talk.
Thank you.
And so, yeah, and with that, I think many of us will be talking to you this afternoon. And Peter, I think you can stop the recording.